All right, we're live. So welcome everyone to another installment of TCS Plus. Today we're happy to have Kuikui Liu tell us about spectral independence and its use for analyzing Markov chain mixing times. Before we start, let me maybe start with a couple quick announcements. So the next talk of the semester will not be in 2 weeks due to Thanksgiving. Instead, it will be in 3 weeks when Bill Kuzma will tell us about linear probing. Other than that, let me quickly thank the other TCS Plus organizers, Clément Canon, Rachel Cummings, Anindya De, Sumega Garg, Gautam Kamath, Ilya Reisenstein, Oded Regev, who's somewhere here in the audience, Slil Shram, Noah Stevens-Davidovich, Toma Vidik, and Eric Weingart. So as I said, today we're happy to have Kuikui Liu tell us about spectral independence and its use in analyzing Markov chain mixing times, and a number of recent breakthroughs obtained from this approach. Before giving the floor to Kuikui, let me encourage people to leave or alternatively turn on their video to give Kuikui some visual feedback. Of course, also encourage questions, yet again, question and feedback, question of making this more interactive for everyone. All right, and with that, Kuikui, floor is all yours. Take it away.
Okay. So thank you for the introduction. Thank you all for coming to this, and thank you for giving me this opportunity to speak. Yeah, so as David said, I'll be talking about sort of a new tool to analyze Markov chains. And this is based off of several joint works with a lot of my wonderful collaborators. I plan for this talk to be sort of a fairly high level. I'll try to make it a high level overview of like all the work that's happened in this area and give you a sense of like also the future directions, all the exciting directions that that can be explored. Okay, so let's begin. So a very common problem that people encounter throughout like statistics and computer science is you're given some probability distribution mu, typically in high dimensions. Typically, it either has an exponentially large or an even infinitely large state space, and your goal is to compute like probabilities of various interesting events, or compute interesting statistics, or basically expectations of various functions under this probability distribution. Okay. Now, the common approach to do this is to draw a whole bunch of samples from your distribution mu, and then return sort of the empirical mean, and then hope that the law of large numbers lets you say that, okay, you can get an accurate estimate if you take enough samples. Okay. And so the question is like, how do you do the sampling? And sort of a very related problem is how do you do the counting? So typically, these distributions mu are given to you in unnormalized form. And so a related problem is to compute the normalizing constant for these distributions. Okay. Now, typically, there is some kind of hardness associated to the counting problem. And so we relax this to allow for approximations. So we're allowed to, at least for the approximate sampling, we're allowed to draw from distribution mu tilde, which is close to mu in total variation distance. Or for the approximate counting problem, we are computing the normalizing constant up to a 1 plus epsilon multiplicative factor. Okay. And it turns out, so this very classic work of Jerem, Valiant, and Vazirani, these two approximate problems are more or less equivalent, at least in many interesting settings. Okay, so throughout this talk, I'm just going to focus on the sampling problem. Okay, and then you might have noticed that I am sort of restricting my attention to distributions which are supported on fixed size subsets of some fixed finite set U. Let me just give you a few examples just to show you this is kind of without loss of generality, and it captures a lot of interesting examples. Okay, so one example is, for instance, spanning trees of a graph. So here, the ground set U is just the set of all edges, and the dimension n. You can think of n as being like the dimension of your problem in some sense. Here, the dimension n is just the number of vertices minus 1, assuming your graph is connected. Okay, so this is an interesting class of examples. Here are a few more. Let's consider, for instance, independent sets of a graph. So here, I want to think of an independent set as being a coloring of the vertices with 2 colors, where the green vertices are the vertices in the independent set, and then the red vertices are the vertices out of the independent set. Okay. Now, in this case, the dimension n is just the number of vertices because you have to color every single vertex. And then the ground set U is just the collection of all vertex color pairs. Okay, so in this case, there are 2n many. The ground set U has size 2n. Okay. And you can imagine that this sort of construction of independent sets generalizes in a fairly straightforward manner. For instance, you can do this for proper colorings of a graph, where again, the ground set U is the set of all vertex color pairs, and n is the number of vertices. Okay, and this construction generalizes. Okay, so I hope I've convinced you that sort of restricting my attention to this setting is kind of without loss of generality. At least it captures a lot of interesting examples that are studied in the literature. Okay, so what is the main approach, or what is one very classic approach to do the sampling? And the classic approach is to do Markov chains or random walks. Okay, so let me just illustrate a very simple one in the case of spanning trees. So here I've collected all my spanning trees at the top. And I'm going to augment the state space to include so-called like the near spanning trees, quote unquote, and where it's basically a spanning tree minus an edge. And then each step I do the following local update, which is first I remove a uniformly random edge. Let's say I go to this one. And then out of all spanning trees that I can complete this near spanning tree into, I pick one with probability proportional to the distribution mu, or I guess in this case, just uniformly at random. Okay. And I go here. And so this sort of two-step down-up motion induces a walk on just the spanning trees. And you can just keep repeating this random walk. Okay. Now in the case of spanning trees, this is this Markov chain has a name. It's called the basis exchange walk. This actually very general down-up construction is also called the down-up walk. And it's sort of one of the simplest Markov chains that you can come up with. Okay, so let me also illustrate this for independent sets. So here I've collected all my independent sets, and I augment the state space to all of the partial colorings of the vertices. And then in each step, what I do is I remove a uniformly random vertex color pair, or in other words, I uncolor a uniformly random vertex, and then I complete this partial coloring into a full coloring I go up with the probability proportional to the distribution mu. Okay. And again, I just run this down-up motion. And in this case of the independent sets and also proper colorings, this covers sort of another very famous Markov chain studied in the literature called the Glauber dynamics. Or if you come from a more like a machine learning kind of background, this is often also called the Gibbs sampler. Okay. So all of this is to say that also the setting, the simple Markov chain, the simple down-up random walk, captures a lot of heavily studied Markov chains in the literature. Okay, so two important things to note. The first is that by construction, the distribution mu is the stationary distribution of this Markov chain. So what does that mean? It means that if I sample a random element from mu, and then from that random element, I take a random step according to this Markov chain, then the output of this random process is still distributed according to mu. So in other words, mu is sort of preserved under this Markov chain. And then the second thing to observe is that, at least in all cases that we'll consider, for instance, spanning trees, independent sets, and proper colorings, this Markov chain is going to be connected. Okay, so you can walk from any state to any other state. Okay. Now, these two observations are important because what it means is that if you start from any initial distribution of the Markov chain and evolve it according to this Markov chain, it will eventually converge to the stationary distribution mu. Okay, and so the sampling algorithm is then just to sort of run this Markov chain sufficiently long. And how long should you run it? The amount of time you should run it is something called the mixing time, which is the following. If you look at sort of the worst starting state, you look at the minimum time t, such that the distribution of the Markov chain started at state x at time t is close to the stationary distribution in total variation. Okay, so this is called the mixing time. And the main question is, well, under what conditions can we bound this mixing time by a polynomial in like the dimension and the size of the ground set U? Okay, so in the context of independent sets, for instance, we want to bound this mixing time by a polynomial in the size of the underlying graph. Okay. Okay, and sort of the thesis that I want to put forward here is that if the distribution mu satisfies a kind of limited correlations property, then the simple Markov chain mixes rapidly. Okay, so a priori, this might look a little bit strange to you, especially I understand this is sort of a TCS kind of audience where we know that there's a connection between fast mixing random walks and sort of expansion, quote unquote. Okay, but I'll mention this a little bit later on, which is that there is a sort of an intimate connection between quote unquote limited correlations and sort of a kind of expansion condition. Okay, and perhaps another example that you might keep in mind is, for instance, the simple random walk on the hypercube, or the or more in generally just the simple random walk for product distributions, and where you sort of pick a random coordinate and you resample that coordinate. Now in that case, limited correlations. I mean, the correlations in such a distribution you have no correlations at all. The correlations are 0. And in that case, you also have that the simple Markov chain mixes very rapidly. Okay. And I'll talk a little. I'll make this a little more precise later on in the talk. Okay. So the outline of my talk is the following. So I'm going to introduce this notion called spectral independence, and this is sort of our notion of limited correlations. I'm going to talk about some local to global phenomena that these objects exhibit, or basically how to get from spectral independence to rapid mixing. I'm going to talk about some applications, and then I'm going to talk about sort of a big laundry list of methods that we now know that sort of give you spectral independence. Okay. Okay. So any questions about the setup? Okay. Okay. So let's get into spectral independence. Okay. So here I'm going to define a matrix where I'm going to think of this as a matrix of correlations. Here, the rows and columns are going to be indexed by the elements of the ground set U. And the ijth entry is going to be given by this difference of conditional margins. Okay. So you can think of this as a correlation matrix. I personally like to think of this as more of like an influence matrix, because you're acting how much does changing, knowing the status of element I, influence the marginals for J. Okay. So we have a matrix, and we can ask about eigenvalues, and we'll say our distribution is spectrally independent if the largest eigenvalue of this influence matrix is upper bounded by this quantity 1 plus eta. Okay. And as sort of as an aside, this notion of spectral independence originates from sort of a spectral notion of this recently emerging area of high dimensional expansion. Okay. So there, what you do is you have this like gigantic global walk, this gigantic Donald block that you want to analyze. And you kind of, in a very vague sense, or roughly speaking, you break it into a bunch of quote unquote local random walks. And these local random walks are going to be random walks on the ground set U, where the transitions are given by conditional marginal probabilities with some normalization. Okay. And so there, sort of what the goal was to, if you have sort of an expansion condition for, like in the usual sense, like an expansion condition for these local random walks, then you want to say that, okay, that will then give you some expansion condition for like the global Donald block that you care about. Okay. And this is exactly what spectral independence also sort of quantifies. So there is a very precise relationship between sort of the spectral structure of these influence matrices and these local random walks. Okay. And in particular, if you have spectral independence, what it says is that these local random walks are very fast mixing. They mix in basically one step. Okay. And then sort of using sort of some technology in the high dimensional expander literature, you can then go from very fast mixing these local walks to polynomial mixing of this global Donald block that you want to analyze in the end. Okay. So, okay, I'm not going to need to use this notion of high dimensional expansion or these local walks later in the talk, but I did want to just mention that there is this connection. This is kind of how we came to this notion of spectral independence, and that you can view all this through the lens of sort of expansion, like spectral expansion. Okay. Okay. So let me show you a couple examples of this. Okay. So let's, for instance, look at the independent sets of this 3-vertex graph here that I'm going to use as sort of like one of my running examples throughout the talk. So here the influence matrix is going to be a 6x6 matrix corresponding to the six vertex color pairs. Okay. So let's look at, for instance, the influence on this vertex being colored green to this vertex being colored red. So the first thing to notice is that because if you condition on this vertex being colored green, this forces its neighbors to be out of the independent set. So this forces in particular this vertex here to be colored red. So this conditional marginal here is going to be equal to 1. And then now, out of all 5 independent sets, exactly 3 of them, these 3 here, have this vertex being colored red. And so you get that the influence is 1 minus 3/5 or 2/5. Okay. So this is one of the influences. You can also look at the influence of sort of the other way around. And if you compute it, you'll get this number 2/15. Note that these two numbers are not the same. Okay. So in the end, you get, if you compute all the entries of this matrix, you get the following. So you'll notice that first that this influence matrix has, positive entries, negative entries. It's not a symmetric matrix. But sort of because of this connection I said earlier with local random walks, it will still have real eigenvalues. And if you compute the eigenvalues of the influence matrix in this case, you'll get these numbers. Okay. Okay. Sort of as a second example, let's consider the case that the distribution mu is a product measure. So in this case, you have no correlations. So all the off-diagonal entries of this influence matrix are going to be 0. And so in this case, the distribution mu is going to be 0 spectral independent. So this is sort of a very good case. Sort of a second case, let's say if you have this property known as negative correlation. So negative correlation is sort of this very heavily studied property in probability theory, which has lots of nice implications, for instance, to concentration of measure, and also has implications to rapid mixing of random walks. Basically what it says is that in the language of spectral independence, that all the off-diagonal entries of these influence matrices are going to be non-positive. Okay. And it turns out, if you do it just some quick calculations, this implies spectral independence with parameter eta parameter equal to 1. So this is still a very strong spectral independence. So in general, you want this eta here to be as small as possible. Okay. And then as a third example, let's go to the other extreme. So let's say the distribution mu is supported on 2 disjoint sets. Okay, let's say 1 through n and then n plus 1 through 2n. Okay. Then in this case, if you know sort of the status of like one of these elements, say the element 1, then you know exactly which set you sampled, right? If I know 1 is in the set that I sampled, then I know that I sampled this set and that I didn't sample this set. So you can imagine that all the influences are very large. And indeed, the influence matrix is given by this matrix of 1s and minus 1s, basically, with some scaling by 1/2. And if you compute the largest eigenvalue of this matrix, you'll see that it's very large. It's linear in n. So this is sort of the bad case. Okay, so you should think of like when your state space is like very disconnected, you will have bad spectral independence. Okay. Okay, so now I want to tell you about how to get from spectral independence to rapid mixing. Okay. And to do that, I need to first strengthen this notion of spectral independence to encompass all conditional distributions, okay? So condition on any subset of the elements T to be in the set that I sampled. I want that the influence matrix of the resulting conditional distribution to also have maximum eigenvalue upper bounded by this parameter 1 plus eta. Okay. Okay, so basically it's just the previous notion of spectral independence I said, but for all conditional distributions. Okay, and so the first theorem, which is really due to 11 Lau, says that if you have spectral independence with parameter eta, then you get that this simple Markov chain that I mentioned earlier mixes in n to the 2 plus eta steps. Okay, so in particular, if eta is a constant independent of n, you get polynomial mixing for this simple random walk. Okay. And let me also mention that there were sort of weaker versions that were known earlier prior to this. Okay, so what this result suggests is that if you have spectral independence, then you can get rapid mixing. One unfortunate feature of this result is that it depends. The mixing time depends really sensitively on how much you can, how good of a bound you get on the spectral independence. Okay, so if you have eta is like 4 or 5, then you get like n to the 6 or n to the 7 algorithm. Okay, so which is polynomial, but kind of not very practical. Okay, so I want to tell you about a second local-to-global result. And for that, I'm going to restrict my attention to so-called graphical models. Okay, or I guess some people in the machine learning community might also call these like Markov random fields. Basically, it's just the following. You have some input graph G, okay? And the distribution is just, you can think of it, a graphical model is just a collection of random variables, one for each vertex of the graph, where you have the following conditional independence property, okay? Sometimes also called the Markov property. It just says the following. If you take two pair of vertices, U and V, or one pair of vertices, U and V, and you condition on the values of these random variables on a separator that's on this graph. So basically, once I condition, I basically disconnect these two vertices, U and V. Once I do that, then these random variables, XU and XV, are independent of each other. Okay. So for instance, this is the case with independent sets. So if I have this 3-vertex graph here, and I condition on knowing the value of this, the assignment for this vertex in the middle, let's say it's out, then it's the same thing as like deleting this vertex from the graph. And in the resulting graph, these two vertices are disconnected and they basically don't influence each other at all. Okay, so their assignments are independent of each other. Okay. Okay. So just to give a slightly more technical definition, which our result applies to. So here you have a distribution where basically you have the product over the interactions across edges, and then at times also some a product over weights on the vertices. Okay, and you don't have to parse this like technical definition. Just keep in mind a few examples. One is being independent sets. If you've heard about this model called the Ising model of magnetism, this also falls under this framework. Proper pairwise also is an example of graphical model, and so on. So basically, this is a large class of distributions that captures a lot of objects that we frequently encounter in computer science. Okay. Okay. And so the second local global theorem says the following: if I have spectral independence where this eta parameter is bounded by a constant independent of n, then this global dynamics, or just the simple random Markov chain, mixes in actually n log n steps with constant depending on this parameter eta and the maximum degree of the graph. Okay, so this theorem only applies to a bounded degree graphical models. Okay? But notably, it has sort of the optimal dependence on n here. Okay. Okay, so this is sort of the second local global theorem. Yeah, as I mentioned, it has optimal dependence on n. And there also have been a lot of recent developments sort of improving or like proving extensions of this result in many settings. Okay. I'm not going to go into detail there. Okay. Okay, so any questions about sort of like local global theorems or how to get from, spectral independence to rapid mixing?
Yeah, a quick question about the hidden constants in the theorem statement.
Okay.
What are the kind of dependencies on eta and delta in these statements?
Okay, I was hoping you wouldn't ask a question like that because the constant is rather bad. It is exponential in the maximum degree and also this dependence and in this parameter eta. But I think okay, so there have been recent works that sort of improve upon these constants a lot. Okay, so and I'll mention something later on, at least for a specific model, but it can be improved, and I think there's work to be done there.
I see. And the follow-up works still have this exponential dependence, or some of them decrease this with polynomial? Or? Okay, so this might be a bit technical. So this work here improves the constant. Actually, these two work, and this work improves the constant in the case of. So, I guess. So previous works try to bound sort of like the spectral gap, and this only gives you like sort of n squared mixing. So you get sort of n squared here, but get a much better constant here. And then there have been more sophisticated techniques recently that sort of really improve upon these constants, but they sort of don't apply to, at least for now. I mean, I expect their techniques generalized, but they don't apply to all graphical models so far for now. Okay, so it's a little bit technical, but yeah. Got it. Thanks.
Yeah. Okay. Any other questions? Okay. Okay, so now let me sort of mention a few applications of this sort of machinery. So I believe my advisor Cheyenne actually gave a TCS Plus talk about 2 years ago on sort of the application of this technology to sampling basis of matroids. But since then, this area has really taken off and has now a lot of models have been studied through this lens. Okay, and so throughout this talk, I'm probably just I won't have time to mention all these, but I'm gonna focus on just probably just matroids. I'll mention it briefly, and then independent sets, and then the colorings. But I just wanted to put this up here just to show you that there have been lots of developments for lots of different models using this machinery. And then before I get into these concrete applications, I also want to mention that these kinds of notions of high dimensional expansion have really had a lot of applications outside of Markov chain mixing as well. So for instance, there was some recent work on proving sort of concentration inequalities using this. You can also get guarantees for local search algorithms for discrete optimization. And then also using sort of other notions of high dimensional expansion, you can get lots of really cool results in property testing and codes. So actually, I think just last night, sort of this breakthrough work on locally testable codes was posted on arXiv, and it uses sort of a notion of high dimensional expansion. Okay. And so all this to say is that so this area of high dimensional expansion, which is sort of still a very young field, has already had a lot of applications, and sort of yeah, I mean, it'd be really cool to see what else it can do. Okay, so now I'll talk about a few concrete applications. So I guess I mentioned earlier that Cheyenne has already talked about this rails for matroids, so I'm not going to spend too much time on it. If you don't know what a matroid is, that's totally fine. You can just keep in your mind that it's sort of like this, sort of a generalization of the case of spanning trees, or collections of linearly independent vectors in a vector space. Formally, it's a collection of subsets of some fixed size of some ground set U, satisfying some very nice exchange property. Okay. And so what we showed in 2019 is that the uniform distribution or basis of matroids are spectrally independent with parameter 0. So this is like basically the best kind of spectral independence that you can get. And from that, using these local or global theorems, you can get that sort of the basis exchange walk mixes in polynomial time. Okay. And sort of using more sophisticated technology, we can now get like n log n mixing. It actually implies sort of the current fastest algorithm for sampling spanning trees. And it also has an extension to sort of a discrete analog of log concave distributions. Okay. And then it also has lots of nice applications to like reliability problems, to credit networks. It has helped us understand a lot about the geometry of matroids, in particular the combinatorics of the matroid polytope, and has other applications to like DPPs and so on. Okay. All right. So the second application is the independent sets, and here I'm gonna weight each independent set by some parameter lambda to the size of the independent set. Okay. So this is a classic statistical physics model called the hardcore gas model. It's sort of like a discretized version of a slightly more realistic continuous gas model called the hard spheres model. And it also has been studied really heavily throughout the literature. I mean, even for very special classes of graphs, studying this problem, there have been a lot of work studying this problem. Perhaps one of the most interesting features of this problem is that it exhibits some kind of a phase transition, okay, in the following sense. So here on the y-axis, I'm going to put sort of values of this parameter lambda. Now, you should think of this problem as being harder if this parameter lambda is larger, because you're going to put the distributions putting more mass on sort of the maximum independent sets, which are sort of hard to find. And you should think of this problem as being easy when this parameter lambda is small, because you're going to put all of your mass on sort of the small independent sets, like the empty set. Okay. Now, so for a long time, there's this sort of statistical physics prediction that there is a very sharp phase transition that occurs in this model that sort of very precisely delineates between when you have fast algorithms and when things are hard, like provably hard. Okay. And sort of there was a very long line of work that sort of tries to sort of pinch this thing from both sides, try to get try to rigorously establish this phase transition. Okay. So beginning with this work by Luby and Vigoda in the 90s, what they already knew back then is that for lambda above some constant divided by the maximum degree, it's actually NP hard to do the sampling. And sort of over the years, this was gradually brought down to this critical threshold. On the sort of algorithmic side, it was also known to Luby and Vigoda that for lambda below, say 1 over the maximum degree, that you have fast mixing of this simple Markov chain. And then this was also gradually improved over the years. And previous works could get up to this critical threshold, but unfortunately had to make sort of fairly restrictive assumptions on the input graph. So they have to make assumptions like that the graph has certain growth conditions or has certain girth conditions. So, and the previous state of the art for general graphs of bounded degree was sort of stuck at sort of this like 2 over the max degree threshold. Okay. So in a very recent line of work, starting with joint work with Nima and Cheyenne, we managed to sort of get all the way up to this critical threshold without making any structural assumptions in the graph. And it started off with being a pretty bad writing time, but it's still polynomial. And then this is gradually brought down to n log n. And notably, sort of all of these recent techniques have used spectral independence, and then all the prior techniques use a different technique called coupling. Okay, so let me sort of say something a little more formally. So I'm going to assume that this lambda here is sort of below this critical threshold, and sort of the gap here is this little delta here. Okay. So in sort of initial work with Nima and Cheyenne, we showed that we have some spectral independence, which is kind of bad, but at least it doesn't depend on n. And what this implies is that this simple Markov chain mixes in polynomial time with some really horrible exponent, depending on this little delta here. Okay. And then in a follow-up work with Zhongchen and Eric, we managed to bring this spectral independence down, sort of like basically the best spectral independence that you can hope for. And then this using the local to global technology back then, we could get some improved mixing time, which is still kind of bad. And then more recently, we managed to show us that actually we can get n log n mixing using sort of this the local to global theorem for graphical models. We managed to show that basically this simple Markov chain mixes in n log n steps with some bad constant depending on the maximum degree and this little constant delta and this gap little delta. And then let me also mention that there was this really cool work that was actually, I think it was uploaded just like a week ago or even less than a week ago, which actually shows that there is a simple Markov chain algorithm that actually runs at n log n time for even unbounded degree graphs with a constant that only depends on this little gap delta, little delta. And the constant is actually not too bad. I mean, it's exponential little delta, but if I remember correctly, but it's way, way better than what we had before. And it's not exactly the global dynamics, but it's still it's fairly simple and easily implementable Markov chain algorithm. I don't want to get into too much details, but all this to say that sort of this line of work has culminated in sort of now basically like the sort of in some sense like optimal sampling algorithms for this problem. Okay, so I guess as I mentioned earlier, this has optimal dependence on n, and actually for many models such as the hardcore model, this is it's actually NP hard above this phase transition point. Okay. Okay, so now let me sort of say the third application, which is to proper colorings. So here I have a graph G, and I have again this big delta denote the maximum degree of the graph, and I have some number of colors Q. And I'm going to look at the uniform distribution over proper colorings of the graph. Okay. And here there's actually a very big conjecture, which is still unsolved in this area of approximate sampling and counting, which is that efficient sampling should be possible when the number of colors is above the maximum degree plus 1. Okay. So sort of on the hardness side of things, it's known that when Q is basically below this maximum degree, then it's NP hard to do the sampling. Okay. And so this is actually another example of this kind of phase transition phenomena. There's like a phase transition that happens exactly at the maximum degree. Okay. And this is this problem has been like open for many years, and I really hope maybe one of you can work on this and solve this. I don't know. But this is we're really stuck on this problem. Okay. So let me mention just some of the prior works on this problem. And there's been really a lot of work studying this problem. I'm just going to highlight sort of two lines of work, roughly speaking. So I'm going to sort of categorize them as sort of general graphs versus locally sparse graphs. So the first line of work sort of tries to show that for all graphs of maximum degree delta, you can get fast mixing with gradually improving thresholds on the number of colors Q. Okay, and sort of over the years, this is brought down to sort of this like 11/6 minus some small epsilon times maximum degree, and we're sort of stuck here. And so what a lot of people try to do to sort of get around these kinds of barriers was to make additional assumptions on the graph, such as local sparsity. And sort of the reason that's kind of helpful is that, if for instance, your graph is like triangle free, then you kind of have sort of more independence in some sense, and the sort of analysis is easier. And so using local sparsity assumptions, you can get sort of improved thresholds on this, on the number of colors Q. Okay. Yeah, okay. So the sort of these two lines of work, okay, and sort of what we did was, instead of making local sparsity assumptions, we actually tried to analyze the dynamics for proper colorings on a class of graphs called so-called line graphs. If you don't know what those are, that's totally fine. You can think of this as being edge colorings of graphs. Actually, there's a typo here. This should not be edge colorings, but you can think of this as being edge colorings of graphs. Line graphs are they are locally dense. Like the neighborhood of like a vertex is basically a clique. And so what we managed to show is that using sort of this new spectral independence technology, we managed to show that for Q larger than 10/6 times max degree, which notably is better than 11/6, we can get fast mixing of these dynamics. Okay, so as I mentioned, these graphs are locally dense, which is sort of kind of different from sort of this previous line of work of using local sparsity assumptions to get fast mixing. And I suspect that sort of combining our techniques with sort of like, perhaps the methods used by in this line of work on local sparse graphs, we can maybe, break past these barriers for this problem. Okay. Okay. So any questions about applications? Okay. Okay, so now I'm gonna just tell you about some of the methods that we now know that will give you spectral independence. So if you have some Markov chain that you want to analyze, and if for whatever reason the previous techniques were not doing it for you, then maybe you can try to use spectral independence and some of these ideas to analyze your Markov chain. Okay. Okay, so the first method I want to tell you about is the so-called trickling down method. Okay, and it's sort of this like kind of magical phenomenon, which is the following, which is that if you know a bound on the largest eigenvalue of the influence matrix of all conditional distributions from mu, then you can get, in a totally black box manner, some bound on the largest eigenvalue of the influence matrix for mu itself. Okay. I'm not going to say too much more about this, like why this is the case, but I do want to say that this phenomenon sort of suggests the following strategy for establishing spectral independence, which is just that what you do is you condition on a whole bunch of elements of your distribution, all the way to the point where your distribution has very small dimension, like dimension 2. Now in dimension 2, you can kind of sort of analyze things very explicitly. You can kind of write down the matrix explicitly and sort of compute its eigenvalues pretty precisely. And then the goal is then just to use then this trickle down theorem just to deduce in totally black box manner a bound for the spectral independence for every conditional distribution. Okay, so say that again. You just condition all the way until your distribution is very simple and low dimensional. prove a bound for spectral independence there, and then use this theorem to deduce in totally black box manner spectral independence bounds for all conditionals of your distribution. Okay, and it turns out this strategy works out very nicely, for instance, for matroids. Okay, so there you can actually get a constant of 1 there, and in that case, this constant actually doesn't degrade at all as you go down. Okay, so this is a more general theorem that's kind of alluded to, which is that if you have some bound, say lambda, on the spectral independence for all conditional distributions, then you can get some slightly worse bound in a totally black box manner for the spectral independence of your distribution itself. Okay, so this f of lambda is going to degrade as you keep applying this theorem. Okay, but even though it degrades, let me just say that it still has actually a lot of really useful applications. So for instance, in the area of high dimensional expanders, one thing that people are interested in is constructing infinite families of bounded degree high dimensional expanders. And in like almost all, or at least a lot of the constructions, what they do is they exactly use the strategy I said earlier, which is they sort of analyze things after you've conditioned on a bunch of elements to the point where your thing is dimension 2, and then just use the trickle down theorem. Okay, so this is still a very, very useful theorem in that setting. But unfortunately, it is not quite, at least in its current form, applicable to our setting for Markov chain mixing. Perhaps one reason to think about it, the reason why is because typically the dimension of our problem is going to be sort of growing linearly in n. And so you would have to apply this trickle down theorem like n many times. Okay, so let me make things a little bit more concrete here. So let me illustrate this using an example. Let's say look at, say, proper colorings of a graph. And let's say I've conditioned on a whole bunch of vertices being colored some colors, all the way to the point where I'm left with just 2 vertices. Okay. And let's say these 2 vertices are neighbors to each other. And let's say, the colors available to these 2 vertices are the same, just say Q for simplicity. Okay. So I'm using the trickle down theorem. I've conditioned my distribution all the way till I have dimension 2, or basically I have 2 vertices. Okay. Now let's look at what the influence matrix looks like. So I can sort of collect sort of all the vertex color pairs where the vertex is U on one side, and all the vertex color pairs where the vertex is V on the other side. And you can kind of draw a graph to sort of visualize things. So for instance, if you look at the influence between the vertex U being colored some color C and the vertex V being colored the same color C, then you can compute that actually the influence is exactly this number, negative of 1 over Q, corresponding to the fact that once I color this vertex C, this forces the vertex V to not be colored C. And if you compute sort of any other pair of vertex color pairs, you'll get this number. And if you compute the maximum eigenvalue, you'll see that it's roughly of the order 1 over Q. Okay. So why is this bad? The reason it's bad is because, again, as I mentioned earlier, you would have to apply this trickle down theorem roughly order of n many times, right? Because the dimension of your problem is n, your graph has n vertices. And so you would need to start, it turns out, you would need to start with a number of colors scaling linearly. Okay. Now, if you recall, sort of when I mentioned this sort of the big conjecture and also the previous results, what we want is really a threshold on Q that depends only on the maximum degree of the graph, not on the number of vertices. Okay. So applying the trickle down theorem in its current form is not going to do it for us. And this sort of problem sort of comes up more generally for instance, for independent sets and lots of other models. Okay. So now I'm going to tell you about sort of more recent work that we tried to sort of improve upon this result, this theorem, this trickle down theorem. And to state it, let me first sort of rephrase things slightly. So here I've phrased it as sort of a bound on the maximum eigenvalue of these influence matrices. You can think of this as equivalently, you can think of this as saying you have a spectral bound on, like in sort of the PSD order on these matrices, by a multiple of the identity, where you scale it by this lambda parameter. Okay. So now it turns out what you can do is then you can say, well, maybe instead of using the identity matrix, which is giving sort of a uniform bound on all eigenvalues, maybe I can use some other matrix, say M here. And you would have to construct these M's very carefully. But what the hope is that you can use these M's to sort of capture the spectral structure of your influence matrices more tightly, more precisely. Okay. So you get some, if so, it turns out if you have some bound of with some matrices M sub mu condition on I, and you can get some new bound M sub mu, which is some function depending on this, you know, the matrices for the conditional distributions. Okay, I'm not going to get into too much detail of like how to construct these things, but again, the philosophy is sort of the way to improve the trickle down theorem is to try to capture the spectral structure of your influence matrices more tightly using sort of better designed bounding matrices that are not the identity matrix. Okay. And maybe I'll give you just a couple examples of stuff that we've tried so far in the context of colorings. So for instance, if you let M mu be a diagonal matrix, where it's not the identity matrix, where the diagonal entries just are some function of the degree of the vertices. Okay. Now it turns out you'll get some kind of, you'll need to construct this function little f carefully, but it turns out you can. And using such diagonal matrices, you can recover, for instance, the very classic 2 times the maximum degree bound. Okay. And then if you make things slightly more complicated, where you have maybe a diagonal matrix plus a matrix which is very sparse, which is non-zero only on sort of the constraints of your problem. So in the context of colorings, this just means 2 vertex color pairs where you're looking at 2 neighboring vertices and you're using the same color. And it turns out that this also, you can use this to sort of better capture your problem. And you can, we use exactly these kinds of matrices for our result on line graphs. Okay, so I'm not going to get into sort of more detail about this, but so this method has had some applications, and I sort of expect it to have future applications. Okay, so any questions about sort of this trickle down method?
I have a quick question.
Mm-hmm.
So if we can go back, I mean, I guess you didn't quite specify this matrix, but I'm wondering, is there any methodic way to kind of search through these matrices M sub mu or M sub mu condition on I?
Yeah, that's actually a really good question. So right now, we're kind of just, we don't have like a very good principled way to design these matrices. It's kind of a challenge, right? The challenge is sort of, you want a matrix that sort of tightly captures your spectral structure, but also is convenient. You can bound its max eigenvalue conveniently, right? So, and that's why here, for instance, we chose to use a matrix with which is sparse. But I mean, it's a really interesting question where it's like, how can you design these matrices in a principled manner that maybe applies, more general? Yeah. I would say that's a nice open problem. Yeah. Okay. Any other questions? Okay, so now let me tell you about sort of a second nice method called sort of this, using the techniques from this area called geometry of polynomials. Okay, so this area of geometry of polynomials is sort of, I would say, is captured by this this general philosophy, which is if you have a distribution mu, then you can encode this distribution via a generating polynomial. And then sort of what you want to do is you want to sort of relate sort of nice analytic properties of this generating polynomial to sort of the probabilistic and combinatorial properties of your distribution. Okay. So let me illustrate maybe a few examples of this kind of approach. Okay. So I have a polynomial, and in particular, I can ask where the roots of this polynomial are. Okay. So here I've drawn like the complex plane. Now it turns out if I have a polynomial which is zero-free in the entire upper half plane, then this very beautiful result of Borchea, Brandon, and Liggett shows that you have your distribution is negatively correlated. Okay, so this is some nice correlation property of your distribution mu, and this is implied by sort of a nice analytic zero-free property of your generating polynomial. Okay. So I'm just trying to give you a sort of a flavor of the kind of results in this area of geometry of polynomials. Okay, so this is one example of such a result. Here's another example. So here, again, here I've drawn a complex plane. And now let's say I have some wacky zero-free region, okay, just with some crazy boundary, okay. Now it turns out there is this actually really beautiful work of Barbanach, and actually there's a long line of work here using this method, which says that if you're within sort of a zero-free region and you're sort of away from the boundary of this zero-free region, then you can get sort of efficient approximate counting and sampling algorithms. Okay. So he actually there's this very general method. It's often called the interpolation method. It has several nice features. So for instance, it's actually a completely deterministic method, at least regarding if you're trying to solve the approximate counting problem. It also it works for like complex inputs in the sense that, you know, when you want to compute this, when you want to evaluate this generating polynomial at complex inputs. But it sort of has two disadvantages. The first is that the method is like fairly complicated to implement. And the second is that actually the running time is polynomial with a bad, kind of a bad exponent for, you know, problems like graphical models. And it's actually quasi-polynomial in general. Okay. But nonetheless, sort of the message here is that if you have a nice zero-free region, then you can get actually efficient approximate counting and sampling algorithms. Okay, like polynomial time, approximate sampling and counting algorithms. Okay. Okay. Okay, but sort of this. But what you can ask is, well, if you have, say, a zero-free region, does this imply rapid mixing for a simple Markov chain? And indeed, such results were shown previously, for instance, in this work of Nima Cheyenne and Alireza. They showed that if you have zero freeness in this upper half plane, then you can get that a simple Markov chain mixes rapidly. Okay. And then subsequently, using this like sort of spectral independence technology, there was a more recent work which showed that if you have zero freeness, not necessarily in an entire half plane, but in like a sector where the angle here, or like the aperture of the sector is like a constant independent event. In that case, then you can also get a rapid mixing of a simple Markov chain using this like spectral independence. You can show that actually this correlation matrix has a bounded maximum eigenvalue. Okay. And then even more recently, we had this work with Zongchen and Eric, which generalizes this even further, which says that if you just some zero-free region, okay, it can have some crazy boundary, and then as long as you are away from the boundary, then you can get spectral independence and hence rapid mixing for a simple Markov chain. Okay, and the constant here depends sort of inverse polynomially on this gap little delta here. Okay, so all this to say is that, so just to summarize, if you have a nice zero-free region, which is an analytic property of your distribution mu, okay, or analytic property of the generating polynomial of your distribution mu, then you can get sort of a bound on the spectral independence and hence fast mixing of a simple Markov chain. And this has had some applications, and I expect this to have like more applications in the future as well. Okay, I guess I'm running a little bit low on time, so I'll probably skip, I guess, the only proof, I guess, simple proof I have in this talk. I guess I have 5 minutes, is that right?
Give or take, yeah.
Okay, sounds good. I guess I want to leave some time for some questions. So, okay, so I guess there's this third method, which is called correlation decay, okay, which sort of says the following. It says that your matrix has sort of a nice structural property. It says that for, and this only really applies to like sort of graphical models, but what it says is that if you have two vertices, which are far away from each other in the graph, then their correlations should be small. And in fact, actually exponentially small in the distance between them. Okay, so I like to sort of draw this picture, at least for independent sets, which just says that if I have two vertices that are neighbors of each other, then their influence might be large, right? If I know one of the vertices is in the independent set, this will force the other vertex to be out of the independent set. But if they're far away from each other, then so this vertex doesn't care whether or not this vertex is in the independent set or not. Okay, so you should think of this correlation decay as being sort of this nice structural property of this influence matrix. And in particular, you can use it to bound. You can also use it to bound the spectral independence of the distribution. Okay, and this has a lot of applications. For instance, to like various statistical physics models. This property of correlation decay actually is actually fairly crucial in the sense that, at least for instance, for the hardcore model, it turns out if you do not have this correlation decay property, then it is hard to do, like NP hard to do the sampling. And so this correlation property in the context of graphical models turns out to be fairly crucial. I do want to mention that one nice thing about correlation decay is that it also comes with an algorithm in a similar way to, if you have, I mentioned earlier, if you have zerofreeness, then Barvanok has this interpolation method for approximate counting. Here, if you have correlation decay, you also have an algorithm, often called like the correlation decay algorithm, which has a lot of the similar features to the interpolation method. It's a completely deterministic algorithm for approximate counting. And furthermore, it has sort of two downsides. Mainly, it's complicated to implement, and it has sort of a running time which is exponential in log of the maximum degree. Okay. But sort of using this implication that correlation decay implies, spectral independence, you can get fast mixing, and in particular, you can get fast algorithms for sampling. Okay. And in some sense, sort of looking at sort of the previous two techniques of geometry of polynomials and correlation decay, what I said, to summarize what I've said so far, is that basically correlation decay and sort of zerofreeness implies fast mixing for a simple Markov chain. Okay, so sort of in this field of approximate counting and sampling, which is where I come from, these three are sort of like the main methods. Roughly speaking, these are the main methods for approximate sampling and counting, which we have for which we have provable guarantees. And sort of using this lens of spectral independence, what you can say is that sort of correlation decay and whenever correlation decay and interpolation work, so do simple Markov chains. So in a certain vague sense, this also kind of unifies all of these existing approaches to approximate sampling and counting. Okay. I mean, there's still lots of interesting questions about sort of connections between these two, and sort of perhaps like the converse directions. But if you just care about algorithms for sampling and counting, basically spectral independence sort of unifies these three approaches in some sense. Okay, so I'm not going to have enough time to show you sort of the fourth method, which is called coupling. I do want to wrap up by just sort of, again, showing you sort of like the thesis that we follow in this talk, which is that if your distribution has sort of a limited correlations property, then this implies that a simple Markov chain mixes rapidly. Okay, and in particular, we now have lots of methods that give you spectral independence. Okay, and we also now know that spectral independence implies, and also other notions of high-dimensional expansion implies sort of lots of other nice properties, like optimal mixing, concentration, and so on. So now let me just wrap up by showing you some future directions for research. So the first question is just like, are there new distributions that we can sample from using this technology? And so, for instance, there are lots of major open problems in this area of approximate counting and sampling. For instance, I mentioned one being proper colorings of graphs, but there are lots of others. And likely, if you want to make progress on these problems, you probably also want new methods for obtaining spectral independence. Okay, so the new methods to obtain spectral independence. I guess some other questions include like, is there sort of an average case spectral independence where like you don't need a spectral independence for every conditional distribution, but maybe, you know, maybe most conditional distributions. Does this technology have any implications for like deterministic algorithms for counting? And also, are there any connections with sort of this or recently emerging field of sort of studying like the sampling version of the Lovász local lemma? I mean, these are all, are there any connections there basically? So I would say, there are also lots of other interesting questions, but these are just a few that I wanted to highlight. Okay. And it would be great to see progress on any of these. Okay, so I guess I should probably stop. I do want to advertise. I was asked to advertise one thing, which is that next year there will be a summer school on spectral independence and its connections to Markov chain mixing times, organized by Danilo Stepankovic, Prasad Tatali, and Eric Vakoda. It will take place on UC Santa Barbara, which has a very beautiful campus. And there's a website where if you're interested, you can find more information. Okay, so I'll stop here. And thank you so much for your attention.
Thanks a lot for a great and enlightening talk. Let's maybe open the floor for questions. Okay, let me get the ball rolling. If you could go a couple of slides back, maybe.
Oh yeah, sure. Oh, sorry.
So for the connections, oh wait.
Which one?
I guess this whole notion of spectral independence seems to be a very powerful tool for approximate counting and sampling. And you mentioned maybe a question about applications for maybe algorithmic versions of the Lovász local lemma.
Oh, this one, huh?
Yeah. Do you have any sense of other areas where this might be useful, or is this just kind of like the most? I mean, you'd mentioned the applications to Lovász local lemma. Do you think there's other algorithmic problems where this could be useful?
Yeah, actually, that's a good question. So, I mean, this is all very speculative, but perhaps there are other algorithms used in statistical inference, like maybe variational inference or like leaf propagation, that maybe these techniques can be useful for. Mm-hmm. I'm not sure. I haven't really thought about it. I'm just saying stuff. But I mean, I'd say that's another. I mean, or even just generally other inference algorithms that people encounter in machine learning. That'd be interesting.
Got it. So I'll just mention, one of the tools you use to show spectral independence, this correlation decay, has, for example, had this slightly surprising new application in online algorithms, which is, as you know, I'm into. So I think there might be some room for kind of exchange of ideas between these subcommunities.
Oh, yeah, for sure. I'd love to hear more about it. I'd love to chat about it.
Let's chat offline, maybe.
Yeah, sounds good.
Looks like people are out of questions and are keen to go read up on some of this rich literature. So with that, let's thank Kuikui one more time.
Thank you, everyone.